In this next example, we have how many different words can be made using all the letters from the word Mississippi. First off, how many letters do we have in total? We have 11 letters in total. So let's jot that down somewhere. So we have 11 total. Now we got to figure out what do we have repeating. So let's do this a bit more organized. So we have 11 factorial. Sorry, that's my factorial. It's going to be divided off all the repeating letters. So let's do color coding. So how many letter I's do we have? We see one, two, three, four. Four letter I's. So I'm going to go 4 factorial, and this one represents all your I's. The next letter I see, let's talk about the letter S's. How many S's do we have? We have one, two, three, four. 4 S's. So here I'm going to go divide off another 4 factorial, and these represent all your S's. Finally, we have P and P, so you have 2 P's that are repeating. So it's going to be 2 factorial. So in my denominator, I have 4 factorial, 4 factorial, 2 factorial. Again, plugging all this in on your calculator, you should end up with 34,650. In the next example, example 9, how many permutations of all the letters of the word red deer begin with the letter R? So in this case here, I'm going to switch over to something like FCP, because if I want to begin with the letter R, I can do something like this. Well, first off, how many letters do we have in total? We have 7 letters in total, so I'm going to draw 7 blank lines. So 1, 2, 3, 4, 5, 6, 7. We want the word to begin with the letter R. Well, R is going to go right here. How many letter R's do we have in total? We have 2 options there for R. So that means in this next slot here, it could be any letter. Could be another R, could be any of the other letters, but it could be any letter here. So how many letters do we have left over? We have 6 letters left over. Then I'm going to go with 5, 4, 3, 2, and 1, because then we'd run out of letters. From here, from our FCP, I'm going to divide off all my repetition. Well, what's being repeated? Well, we had 2 R's, so that's 2 factorial, and that one represents your R's. I see E's and I see 3 E's, so it's going to be 3 factorial for your E's, and I see 2 D's. So 2 factorial, and that would represent your D's. In total, what does this get you? Numerator, if you multiply that all together, you should have 1,440. Denominator, that gets you to 6, and 4 and 4 make 24. There we go. And dividing these two together, you get a total of 60 permutations with the letter R right at the beginning. In this next example, example number 10 here, we have a family of 6 are getting ready to take a family picture. How many different arrangements are possible if the mother and father have to sit next to each other? Well, if you have a family of 6, again, I'm just going to do a variation of FCP here. If you have a family of 6, I can do 1, 2, 3, 4, 5, 6. The mother and father have to sit next to each other, so this one could be mother, this one could be father, and that's right next to each other. Okay, so I'm going to put a box around it because this is right next to each other, and that condition is a very specific condition. They have to be next to each other. If they're next to each other, the other seats left over are all the children. So let's call them C, C, and C for children. So where can the mother and father sit? Well, the mother and father could be mother, father, or father, mother. So there's 2 options right here for the mother and father. So I'm going to say that there's 2 factorial because there's 2 options. It could be mother, father, or father, mother. So 2 factorial. And they can sit in how many different positions because they have to sit together. So if I just count out my positions, so they could be at the beginning. So this is position 1. They could have been right in between these 2 children, or between these 2 children, between these 2 children, or right at the end. So really, how many positions can this mother and father pair be in? They could be in this first position, second, third, fourth, or fifth position. So here I'm going to multiply this by 5 factorial because that's going to be all the number of positions where the mother and father can be together. So if we run this now on our calculator, you should end up with 240. In example number 11, it's asking you how many arrangements of 6 children, Anne, Bob, Carl, David, Emma, and Fran, seated in a row are possible if Anne, Bob, Carl must sit next to each other. So again, let's set up something like 6 dashed lines. 1, 2, 3, 4, 5, 6. We have Anne, Bob, Carl all next to each other, so we have Anne, Bob, Carl all next to each other. You still have David, Emma, and Fran who could potentially sit in that order there. Again, if this group of 3 have to sit together, I'm going to box them off, okay? Meaning that they have to be arranged in some sort of group of 3 here. Well, this group of 3 could have been Anne, Bob, Carl, and Carl, Bob, Bob, and Carl, Bob, Carl, and it could be any of those arrangements there. Really, this is in here 3 factorial. So those 3 people and Bob Carl have 3 positions that they can sit in. Here, if they're together though, they can move in how many other positions? They can be in this first position here, position number 2, position number 3, or right at the tail end there, so that's the 4th position. So we're going to go 3 factorial multiplied by 4 factorial because they have 4 different spaces that they can sit in. So here, if I multiplied that together, in total I would get 144 arrangements of having just Anne, Bob, Carl together, and then David, Emma, Fran in some sort of order. In 11a, this is a continuation of number 11. How many arrangements are there if Anne and Bob must not sit next to each other? So this one here, I'm going to put a star next to this question here because this one is one of these ones where it must not sit next to each other. So the way that I tackle this question here, and there's multiple ways to do this, is I do no restrictions minus the together. So again, what I'm doing, I'm setting up this equation here. I'm going to do a no restriction, and I'm going to subtract off being together, and that's going to then equal the not together. Okay, so again, how many kids were there, or how many people were there? There's 6 of them in total. If there's no restriction on where they need to be, this is just purely 6 factorial. I'm going to subtract off them being together, just Anne and Bob together. Well, if Anne and Bob are together, that's 2 factorial because it could have been Anne, Bob, Bob, Anne, and then they would have 5 positions that they could have sat in, beginning at the front, the 3 middle, and right at the tail end. So that's 5 positions. Here, let's evaluate this. This is going to get us to 720 minus 240. That gets us to a total of 480 options. And so this 480 represents not together. So there are 480 options of Anne and Bob not sitting together. So let's write that down. So 480 arrangements of Anne, Bob not together, and A, B not together. Alright, there we go. Again, could you have solved this in a different manner? Of course you could. You could have used, and I've seen this done here where you could have done, sorry, just splitting up my page there. You could have done something else. You could have done out of the, you'd have, so Anne and Bob are not together, so you can have the Carl, David, Emma, Fran somehow together, so that's 4 factorial if those 4 are sitting together. And then from here, you want to go multiplied by 5, pick 2. And this 5 pick 2 represents the 2 positions that Anne and Bob can be in after that. So here, this would also get you to 480. Personally, I like this option better where you go the no restriction minus together, and usually there's a together question previous equals the not together. In example 12, we have how many different arrangements of all the letters in the word mathematics are possible if the vowels are always grouped together. Well, first off, how many letters do we have in here? We have 4, 6, 7, 8, 9, 10, 11 letters in total. Out of those 11 letters, how many are vowels? How many are consonants? So in here we have A, that's a vowel, E, that's a vowel, A again, that's a vowel, and I, that's a vowel. So here we have 4 vowels. That leaves us with 7 consonants. In total, 4 and 7 make 11 letters in total. So if my 4 vowels are always grouped together, I have 4 factorial. How many positions can these 4 letters be in? Well, if there's 7 consonants, it's going to be at the beginning of the consonants, at the end, and that's 2 positions, and all 6 in the middle. So that's going to be 8 positions in total. So I'm going to go 4 factorial, 8 factorial. From here, this is just like every other previous question. However, I'm going to divide off repetition. And that's probably one of the most common mistakes that people forget to do is divide off repetition. Again, where does this 8 come from? This is 8 arrangements. Or you can call them positions. So, going back to our question though, so we have 4 factorial, 4 vowels all together in some sort of order, 8 factorial, 8 positions where those 4 vowels could be stuck together in between all these other letters. Now we're going to divide off all our repetition. Well, I see A's, I see 2 of them, so I'm going to go with 2 factorial, and that one's going to represent my A's. I see M's, so that's 2 factorial, that's going to be my letter M's. And I see the letter T, so that's 2 factorial, and that's going to represent my T's there. In total, what does this get us? Numerator should have given you something like 967,680. Denominator should have given you 8. Dividing these, we simply get 120,960. In this next example here, example 13, we have how many different arrangements of all the letters in the word calculus are possible so that the C's are not together. So again, C's not together. I'm going to do an example where I'm going to go with C's together and subtract that off from no restriction. So how many letters do we have in total? In calculus, there's 8 letters. So my 8 letters can be in any sort of position, so it's no restrictions, 8 factorial. I'm going to subtract off my 2 C's together, so 2 factorial, in 7 different positions. For both of these though, the one thing I'm missing, divide off your repeating letters. So in the word calculus, we have repeating C's, U's, and L's. So that's 2 factorial, 2 factorial, 2 factorial. And on this side, 2 factorial, 2 factorial, 2 factorial as well. So if you ran these numbers here, on the left you'd have 5,040, and you're subtracting off 1,260. In total, there is 3,780 different arrangements where C's are not together. In example 14 here, we have how many different arrangements using all the letters of the word success that, in part A, only begin with exactly 2 S's, and in part B, begin with at least 2 X's. So, two different questions. Here we go. So, how many letters in the word success here? We have 2, 4, 6, 7 letters in total. If we want to begin with exactly two S's, I'm going to go using FCP, 7 blank lines. 1, 2, 3, 4, 5, 6, 7. My first two begins exactly with two S's, have to be S and S right here. So how many S's do we have in total? Well, in this we had three S's and then two S's. This third position here, because it says begins with exactly two S's, this third position here has to be not an S. Because if you had an S here, then it wouldn't fit in this begins with exactly two. So how many letters are not S's? We have four letters that are not S's. Well, in this fourth position, what can it be? It could be any other letter that we haven't already used. So we already have used up three letters in total out of our seven. So how many letters left over? We have four letters left over. And then three letters, two letters, and one letter left over. So in total, if I multiply all this together, what do I get? I get 576. And most people would have left their answer like this. However, there is one extra step that I need to do to this answer here. It's to divide off repetition. So what it's repeating, we got our repeating s's, so we got 3 factorial for the repeating s's and 2 c's, so 2 factorial. So really, my final answer here should have been 48. And please be aware of this one here. On multiple choice, you could see 576 versus 48, so be aware that you had to divide off repetition. In part B here, it says begins with at least 2 s's. So at least 2 s's means you could have had 2 s's, just like this first case, or you could have had all 3 s's. Or meaning to add, by the way. So I'm going to set up both of these examples here. So if you had 2 s's, so let's do 2 cases. So if you had 2 s's, you'd have 3 times 2 times that 4 times 4, 3, 2, 1. Of course, dividing off repetition, 3 factorial, 2 factorial. And this here in blue is 2 s's. But we're going to do another case where we're adding on, and we have all 3 s's. Well, if you had all 3 s's, that would be 3, 2, 1, because that third letter was an s. Then you'd have all 4, all 3, all 2, and the last letter left over. And again, of course, dividing off repetition here and here. So this case here is 3 s's. Yeah. And sorry, grammatically incorrect. There we go. If you round these numbers on your calculator, what do we get? On the left here in blue, we would have had 48. And we're going to add on, in green here, 12. In total, we have 60 options that begin with 2 s's or all 3 s's. In our last example here, we have how many different arrangements are possible of the letters of the word oranges if the vowels must be together, and then if the vowels must be together in alphabetical order. So right now, what are our vowels? How many vowels do we have? In total, we have O, A, and E. So we have 3 vowels. So I'm going to go 3 factorial. How many positions can they be in? Well, how many letters do we have left over? I have 1, 2, 3, 4 letters. So that means I have 5 positions that they could have been in. So here, 3 factorial times 5 factorial, this is 720. With the O, A, and E in that order. If your vowels have to be in alphabetical order, well, what's our alphabetical order? We only have 1A, 1E, 1O, so that's only one option for all 3. They have only one arrangement that they could be in. Again, how many positions do we have? We still have 5 positions. So here, this is just 1 factorial times 5, which is just 1 times 5 factorial. 120 total different arrangements with alphabetical order for your vowels. That's the end of our lesson today. If you have any questions, please feel free to ask.